Today's topic is all about the people that contributed to atomic theory. Your learning objective today is to look at the different theories that led to the evolution of atomic theory, as well as the key scientists that contributed. So, in the end, you're going to be able to match the theories to each scientist using either a visual representation or a representation in words. So, we're going to start really far back in history, essentially. We're talking about the Greek model. So, lots of Greek philosophers were theorizing that the world was never changing. It was the same as it always has been. Nothing has changed. Now, along came Democritus, who is then theorized, the smallest form of matter cannot be broken into smaller pieces. So he kind of had this as his Greek model. Just think of a circle. He said, well, it can't be broken anymore. And he called them atomos. Okay, so essentially indivisible. This is the very earliest times of atomic theory. That then came to one of the most famous Greek philosophers, Aristotle, who then said, things aren't changing, but there are some things that our matter is made up of. And he came up with the four essential elements at that time, which was earth, fire, water, and air. So he said all four of those things make up everything that is essential to what is living on the planet. Now, if we then fast forward a very long time after that, we're going to meet up with this man named John Dalton. So John Dalton actually starts the ball rolling. He's one of the first and major contributors to atomic theory. He took the idea that you couldn't break up certain small pieces of matter, and he referred to them as atoms. And what he looked at is he said atoms cannot be created or destroyed. And if they are the same element, they have to have the same size and mass, and every element is different from each other. And when you put those elements together, you create compounds that have different elements bonded, therefore same atoms of the element, but different atoms coming together. So he was one of the very first major contributors, and we call his theory the billiard ball model. Sir Joseph John Thomson was then referred to as the plum pudding. So he's the first person to actually look at the subatomic structure of the particles. So John Dalton was all about the atoms. He's now like, well, there's got to be more to this. So what he ended up doing was he discovered these negatively charged particles that are stuck in a positively charged mass. And he gave them names, and he referred to the negatively charged particles as electrons. So he called his theory the plum pudding model because it kind of looks like plum pudding. I think more of like a chocolate chip cookie, to be honest. You have the positive body mass. So you can see the big circle, the blue circle with all these positives floating around. And then inside you have the negative electrons floating on top. So think of a chocolate chip cookie with chocolate chips throughout. Think of the chocolate chips like the negative electrons, and the positive body mass is the whole cookie. So he came up with that there's going to be more than just the atom, that there's actually stuff called subatomic particles. There you go. Then came Rutherford with what we would call the planetary model. So essentially, he figured out that there's actually no positively charged mass. It's actually a very small center. So in the center of the atom is now what we know are protons and neutrons. And electrons actually orbit the outside of those. How he figured this out is essentially he had an alpha ray, and he took a piece of gold foil and he started shooting alpha particles at this gold foil. And every so often, the particles would bounce backwards and hit a sensor off on the side or behind them. When he thought, well, why is this doing it? They should go through. Alpha particles are really tiny and dense. But it turns out that the nucleus was in the way of some of these alpha particles and shooting it back. So the nucleus is what we call the area containing both the positive protons and the neutral neutrons. Then came Bohr. He's next. And he said it looks more like a mini solar system instead. And he said this is what it looks like. He put a nucleus in the center with your protons and neutrons. And then he made what we would call orbital shells or energy levels around the outside of the nucleus. On those energy levels, those are where the electrons sit. And he came up with his classification of how many electrons are allowed on each shell. So the shell closest to the nucleus is allowed 2, and the shell outside of that is allowed 8, and the one outside of that is allowed 8, and the one outside of that is allowed 8. Now at the grade 9 level, that's as far as you need to know. Once you get into Chem 20 and Chem 30, you will learn a little bit more. So this is Bohr's model. This is what we call a Bohr diagram, which you will also be learning how to create. Schrodinger came up with the electron cloud model. Oh, there we go. Essentially, he called it a charge cloud, and that's kind of more of the present model that we have. He did this based on mathematics, giving probability of finding electrons in places of atoms and distinct energy levels. So for your understanding of everybody we've talked about, all the people that have led us through all of these different discoveries, what you need to know are protons, neutrons, and electrons, the 3 subatomic particles, and where they're located. So if we were to look at a very iconized, like this beautiful picture you see here, you might see it from Big Bang Theory. It's pretty iconic. It's been made pretty famous. This is what we would think of as an atom. But the truth is, it doesn't exactly look like this, but we're going to use this as an example. In the center, the blue and red ones are your neutrons and your protons. The outside is where you will find your electrons. You need to know that for your grade 9 level. Where are protons and neutrons located? Where are electrons located? So if I'm going to take a minute and you guys are going to watch this video quickly about the song of the atom. Now, if we were to look at this picture here, this is what I meant earlier by saying you need to be able to actually connect pictures to people. So this one would be like the Greeks or Dalton, just that big circle, just the atom. This would be much like Thomson's, okay? Thomson's is the example of the plum pudding model. This one's more Rutherford's because he discovered the nucleus in the center, and this is Bohr because you can see the distinct energy levels. That now leads us into the conversation of when you are talking about atoms and you're talking about electrons and protons and neutrons, we also have to think of the bigger picture, okay? And the bigger picture consists of something called the law of conservation of mass. I would like you to write this definition in your notes and then listen to my explanation. So the law of conservation of mass is essentially when there's a chemical change that occurs, the mass of something that is new should be the same as the mass of your original substance. So for example, if I had a toolbox that contained 98 grams, okay, and I wanted to make it equal, I would put 98 grams on the other side of the scale. So that's kind of what you're seeing here in this picture. 98 grams, 98 grams. In a chemical equation, you have the same idea. Whatever is reacting on one side of the equation, such as carbon and oxygen, how much carbon weighs and how much oxygen weighs, when they combine together in a reaction to make carbon dioxide, that carbon dioxide should weigh the same amount as the carbon and oxygen did on their own. That is the conservation of mass. We're saving mass from one side to the other side. You're not adding mass, you're not taking away mass, you are going to have about the exact same amount. Now, in the practice that we will do, you will lose some mass, perhaps due to scientific error, but ideally, the law of conservation of mass, whatever goes in, should come out. That also is part of the definite composition law. So when you have compounds that are pure substances that contain 2 or more elements combined together, they are in fixed and definite proportions. Meaning, this picture right here shows you oxygen with 2 hydrogen, H2, because there's 2 of them, O, 1 oxygen. That is a definite proportion. That creates water. This would be NH3. Okay. NH3 is ammonia. So you have 1 nitrogen to 3 hydrogens. If you add in another hydrogen, it completely changes the entire composition and what it is as a compound. All right. So you have to have them in fixed and definite proportions in order for them to be in that category. Carbon dioxide, 1 carbon to 2 oxygens. Carbon monoxide is 1 carbon to 1 oxygen. Totally 2 different gases. Why? Because they're fixed together in different proportions. So again, this is what you would look at if you were building a model of different elements. So here I have carbon, 2 carbons, an oxygen, and 1, 2, 3, 4, 5, 6. Okay, 6 hydrogens. So you would have C2H6O. And here you can see a bunch of carbons, oxygens, oxygens are the red and hydrogens are the gray. And again, you could count them up and figure out how many are there. So you have 2, 3, 4, 5, 6 carbon, 1, 2, 3, 4, 5, 6 oxygen, to 1, 2, 3, 4, 5, 6, 7, 8 hydrogen. There's probably a hydrogen hiding here. 9. There's going to be one on the other side. 10, 11. There's probably 12. So that would be C6H12O6, which is probably what this is trying to represent, and that would be glucose. So that's just an example of how the law of definite composition works. Same elements, but they're going to actually be completely different things because of the way they're put together. So please make sure that you have the law of definite composition in your notes, as well as the law of conservation of mass in your notes. I'm going to also post this within here to make sure that you watch, and it'll talk a little bit about the laws to help you understand them a little bit further.